Okay, so this is the third lecture. So to summarize, in the first lecture we stated the theorem of the p-adic Eichler-Shimura decomposition for modular curves. And so the players were completed cohomology and higher Coleman theories. And then I explained a diagram. Okay, I mean, last time, by this I mean the first lecture. So I explained this diagram. So this was a Cartesian diagram which involved the Rham period map. Okay, we had okay, so we had the algebraic Shimura variety, and it's the Rham stack, and the Rham flag variety, and it's the Rham stack. Okay, then in the second lecture, George explained what is the completed cohomology and how it can be computed also as the Poetal cohomology of the perfectoid Shimura variety. Okay, and so in this talk will be a continuation on the p-adic side, so in p-adic geometry, and so the main goal of this lecture is to explain and construct another Cartesian diagram that's a bit similar, but that uses an other period map. So the main goal is to prove the following theorem, that we have a Cartesian diagram so here I have the Hodge-Tate flag variety. So that's the Hodge-Tate period map. Here we have the locally analytic vectors, the locally analytic Shimura variety. So I will explain what this is. Then we have the smooth Shimura variety. And here we have some space which is some twist of the Rham stack of the Hodge-Tate flag variety. Okay, so anyway, most of this lecture will be about defining the terms in this diagram and trying to explain maybe not the entire proof, but why this is plausible. Okay, and then using this, what I will then try to explain is how to construct from this diagram the sheaves of over-convergent modular forms for any weight, when the weight is in CP, right? Not just an integer. And to define higher Coleman theories. Okay, and then George in the last lecture will also use many of the ideas behind this diagram, which actually is a continuation of the work of Pan and Rodriguez and many people, to prove or at least explain, maybe not completely prove, the p-adic Eichler-Shimura decomposition I stated in the first lecture. Okay.
Can you say what category are these two?
Yeah, I will say. So this was really this was in the category of sheaves over maybe algebras over Q, okay? Well, that was a scheme, okay? That's the quotient of a scheme by an algebraic group, so that's pretty reasonable. That's maybe the quotient of a scheme by an AND scheme, okay? Like this completion along the diagonal, so this is an AND scheme. But here we are pretty much in some familiar context. Yes, here we will definitely leave this familiar context, and this Cartesian diagram is now really in the world of analytic geometry, or maybe analytic stacks. Okay, so I will spend most of the lecture trying to introduce and define these objects. Okay, yeah. But yes, this is really p-adic analytic stacks. all right. Okay, so what are these objects? So the first thing to do, so indeed, I mean, last time we had the algebraic Shimura variety, okay? So of some level k, and now I anyway base change to get an analytic space, okay, over CP. Okay, so, and now this is what I will now denote by SK, okay? So this is kind of the analytic Shimura variety. Okay, so just to give you some sense of what's going on, if we're doing GL2, okay, then maybe this S GXK was living via the J invariant over A1, which is spec Q of X, okay? And so now what I'm doing is, so I'm base changing, and now I have some SK, and this SK is now, so this is finite, okay, via the G invariant, and now this SK will be finite over the analytic line, okay, and what's the analytic line? This, so maybe I should call this XJ, and so this analytic line is the union of these balls of increasing radii. Okay. All right. Okay, so now in the modular curve case, we have objects which are finite over this A1 analytic. And honestly, I could also work with the compactifications. And in that case, we would have objects which are finite over P1. Okay? P1 viewed as an analytic space over CP. All right. So, So now, so now let me try to define, or recall a little bit the definition of the perfectoid Shimura variety, and also try to start defining this LA and smooth things. All right, so first, so let's denote by SK just the underlying topological space. Okay. And now let's define, so I kind of want my compact to be of the shape KP, KP, okay? And then let me define the topological space SKP to be the inverse limit over small kp of these topological spaces, okay, of finite level, okay? So by definition, the basis of open, of that topological space at infinite level is given by the, let's say, pkp inverse of ukp, where ukp is a quasi-compact open, if I mean I can take it quasi-compact, in this finite level guy, and pkp is the projection of topological spaces. Okay? All right. So we have this topological space, okay? And now we are going to produce certain sheaves of rings over this topological space to get locally ring spaces. So sheaves of rings. Okay, so the first thing we can do is really endo this SKP with a sheaf that I want to call OSKP smooth, and which is just all functions that come from finite level. Okay, so that, I mean, that's clearly a sheaf of rings over this topological space, and so that pair, that locally ring space, I want to call SKP smooth. Okay, all right, so that's something I'm allowed to do. So if you want, what I'm really doing is that I'm taking the inverse limit of the finite level Shimura varieties without completion. Okay. Inverse limit of finite level Shimura varieties without completion. Okay. So, but it's true that here I'm kind of already leaving the world of adic spaces, because in adic spaces the structural sheaf is complete. Okay. But that's still a pretty mild operation, and you can believe that. Yeah, I mean that's just a fancy way to talk about all the finite level Shimura variety at the same time somehow. Okay. So now there's another construction that actually leads to an adic space, and that was explained by George last time, is that one can try to complete this sheaf. Okay, and so one can define another locally ring space, where now we consider that O smooth Kp. Okay, so this O smooth Kp, it comes with a natural norm. So it's just the spectral norm. Okay, so I can I can consider inside O smooth Kp I put a plus, and these are the functions which are bounded by 1. Functions bounded by 1. So this is a subring. Okay, and now you can complete with respect, for the p-adic topology, with respect to that ring, right? I mean, this is now a ZP algebra. Of course, you don't want to complete before you fix a lattice, because otherwise you would get 0. And now you invert P. Okay, and so this is now what's called OSKP. Okay, so and now so now that ring space I really call now SKP without any smooth, and the kind of miraculous theorem, I would say, is that SKP is a perfectoid space, at least, well, I mean, if I guess Gx is abelian. Okay, so that's a theorem of Scholz. So, and it's really miraculous, because this completion, in some sense, it can be very hard to compute, right? Because if you want to actually compute this completion, I mean, I should say that as a remark, is that in principle it is very hard to compute the completion. Because if you want to compute the completion, you really have to compute, for example, maybe I should write. You would have to compute the sections of that sheaf, so you take the plus sheaf and you reduce mod p to the n. But that's actually, this, in principle, the sections here are not, I mean, the sections here in some open, they are not just the reductions of sections. Like, in principle, you have a map like this, right? The reduction mod p to the n map, but there's no reason that this map should be surjective. Okay? Because this, yeah, I mean, no, in general, it's not going to be surjective. So in general, it's very hard to compute this completion. But in principle, it's very hard. But actually, what turns out to be true is that this completion is computable, and actually, there is a basis of open well, I don't, okay, sorry, I think I mean, more could be said, but I may maybe not engage too much with this, but, well, yeah. I mean.
So theorem is for abelian type?
No, I think it's really for abelian type. And now there's the question whether you can extend to the toroidal compactification or not. And I think that this extension is only written for Hodge-type Shimura variety, right? So yeah, I'm just giving some theorem with. I mean, I'm not taking care of the toroidal compactification, okay? But yeah, I feel that if someone was brave enough, he could prove that even the toroidal compactification is perfectoid in the abelian case, and then the exceptional case needs probably a new idea, or I don't know, maybe there's some recent progress, but yeah, I'm not sure. Anyway, okay, yeah, so, well, okay, but that's, okay, so that space, this is so in particular, being a perfectoid space, this is an adic space, okay? All right, so now, one may still want to do something else. So now let's take some open UKP inside some finite level guy, okay? And so we can compute. I mean, well, we can evaluate the sheaf. Sorry. So this completed structure sheaf, we can evaluate it on UKP. Okay? That's, I mean, or I should say on the preimage of UKP, maybe. Okay? And, well, but this will carry an action of KP. Okay, because I mean, on the smooth guy, I had an action of KP, and well, I'm still going to have an action of KP after I do the completion. Okay, so and now since we have an action of KP, it actually makes sense to speak of the locally analytic vectors. Okay, so now we can make sense. So we can look at. We can look for, so first we can just look for the smooth vectors actually, okay? So all those vectors whose stabilizer is an open subgroup of KP, okay? So we can look at, so we can define OSKP smooth, okay? And there's maybe a conflict of notation for 1 second, but then there's a theorem. Okay, so these are the smooth vectors. Okay, and we can define the locally analytic vectors. Okay. Yep. Yeah. Well. Yeah. Okay. Yeah. Maybe. Yeah. And then I can. Okay. Fine. These are the locally analytic vectors. Okay, so again, the smooth vectors are those for which any vector has an open stabilizer, and then the locally analytic vectors, these are those vectors for which the orbit map is a locally analytic function, right? So that means that if you take a small enough compact open, then the orbit map can be written as a converging series, okay? In some chart of Kp, okay? All right. So now, well, clearly we clearly get subsheaves. We get subsheaves, so that I will denote by OLA SKP and O smooth SKP of O SKP. Okay? Well, okay, these are even subsheaves of algebras. Okay, so these are just small exercises that you can check, right? That it's preserved by the algebra structure. Okay, so there's a theorem again of Scholz that actually this O smooth SKP is really the one we just defined above. Okay, so this is really the colimit of the PKP inverse of the finite level guys. Okay, so in other words, it was clear that those functions were smooth, like all the functions that come from finite level. But it might have been that when you complete, and then when you look again for the smooth vectors, you get more smooth vectors. Okay, I mean it's not impossible. I mean you can cook up examples where this arises, I'm sure. Okay, but actually no. Okay, so these are just okay. And well, and now comes the okay, but now we get a new sheaf, okay, that's OLA, so these are the locally analytic vectors. Okay, and so now we can define a new ring space, okay, so same topological space, but new vectors, OLA, SKP. Okay, and so this is what we will call SKPL. So now, I mean, this, okay, I mean, it's kind of a fact, is that actually now so there is more general geometry, p-adic geometry than adic spaces or Berkovich spaces or even Tate sorry?
Wasn't this the definition of the smooth there?
Yeah, but okay, so sorry, I presented the things really badly, but I won't say that the two definitions agree. Like, okay, one definition, yeah, the first definition I gave was to take just as a sheaf of functions, the functions which come from finite level. But then what I'm saying is that if you complete the functions from finite level, then you get this perfectoid Shimura variety. And if you look back for the smooth vectors in it, in principle, you could get more vectors. But I'm claiming that you don't get more vectors. Okay? Okay. So yeah, just I mean, as a side comment is that actually now there's a robust geometric framework in which we can really speak of these, and so these are examples of analytic stacks, and so in particular there's a good theory of coherent sheaves, and yeah, and I think there's been a lot of things developed around there. But honestly, for the talk, it's okay to just think of them as ring spaces. Okay, so I've told you what's the topological space, and it has a sheaf of ring, and I think we can still sell lots of things just with this. Okay. Except at the end, I will then consider the quasi-coherent sheaves over this guy, and there you will have to believe that some theory works, but okay. All right, so fact, so these are analytic stacks. Okay, so, right, but anyway, so the smooth vector, we understand them, okay? We have a description, and so really most of the talk will be about the description of the locally analytic vectors. Okay? What do they look like? Okay. So. Okay, so now, yeah, so we have to, I will give you, I think as a warm-up, 2 toy examples of a similar procedure where we have some kind of, I would say, torsor under a profinite group. Yep? Ah, okay, thanks. So, yeah, so really, you see, the situation was this, right? So we had the Shimura variety at finite level, and then we consider this perfectoid Shimura variety above it. So that's some kind of KP torsor. What, sorry? Well, I've not defined analytic stack, so it's just a remark. You might have heard the. I mean, I just want to say that actually there's more structure than just ring spaces. Okay. Yeah, this is what but I've just defined the ring spaces. But later I will take the quasi-coherent sheaves on these guys and then.
Then you sort of choice. I mean, in this language, as I understand very what this language was, you have to sort of choose what are the complete.
Yeah. Yeah, but these ones will be. I don't think there is an ambiguity because they will be partially proper. So you can view them as. Yeah. Yeah, but you can take the induced structure from QP if you want. Yeah, I mean from QP solid. All right. So okay. So now let's do 2 toy examples. Okay. Okay, so but it's really all about describing the locally analytic vectors. Okay, so in this toy example, my compact KP will be replaced by just the profinite group ZP. Okay, and so now I want to consider the following situation. So let me consider the following algebras. So I consider the continuous functions from ZP to CP. Okay, I consider inside it, the locally analytic functions from ZP to CP. And then inside the locally analytic functions, I can consider the smooth functions from ZP to CP. Okay? And yeah, and maybe, well, clearly all this is over CP. Okay? So now I can take the spectrum or analytic spectrum or whatever. I mean, let's imagine that there is some procedure we're allowed to take, right? So to pass to space. Okay, so I take spectrum. Okay, so now here I get some incarnation of ZP. Okay, so this is the ring space ZP with the sheaf of continuous function. Okay, here I get another incarnation of ZP. So this is ZP with structural sheaf, the locally analytic function. And here I get another incarnation of ZP. This is ZP with the smooth function. And, well, all this lives over, let's say, CP. Well, it's past CP. OK. So now, I mean, this may look like exotic, but actually, this guy over this guy, this is just some limit of more usual spaces. Actually, this guy is just the limit, but the non-completed limit over n of z over p to the nz, underlined, right? I'm just telling you that smooth functions are just the co-limit of functions on z over p to the nz. And similarly, that guy is just the limit over of something that I want to call zp, maybe p to the n analytic. Okay, and so zp p to the n analytic, these would be the functions which have radius of analyticity p to the n. And so that really looks like a disjunct union of balls of radius p to the n. So I'm just covering zp by balls of radius p to the n. And this map is just the fiber, I mean, it's just the connected component map, right? Okay, so this is just a union of disks of radius p to the n. Okay? And in that sense, it make yeah, and so in that sense, it makes sense to say that that actually clearly these two guys are really distinct, and so well, I think it's convincing to say that actually ZP-LA over ZP smooth has relative dimension 1. Okay, just from that picture, right? Here I have disks, okay, and here I have points, and so yeah, so it's relative dimension 1, and so the omega 1 of ZP-LA over ZP smooth, this is really the locally analytic functions on ZP times dz, where z is maybe the coordinate on ZP. Okay, so in particular, ZP-LA is really bigger than ZP smooth, and it has relative dimension 1. Okay, and moreover, one maybe wants to write that ZP-LA divided by the action of the Lie algebra, which is really means that at the level of functions you take the invariants, the vectors which are killed by the Lie algebra, which are therefore the smooth vectors, then this is ZP smooth. Okay, so that, I mean, there's really no much content in all I said. It's just some example where you have, I mean, you have a tower of spaces. I mean, maybe ZP over that guy. This is acted on by the group ZP, which acts by translation on the functions. And then we can look at what it happens if we look for locally analytic functions or smooth functions and see if we can describe these spaces. But of course, in that case, everything is so explicit that, okay, you can just do it. Oh, all right, but it's good to have this example in mind because it will come in strike contrast with the next example. Okay, so now I want to give you a second example. So, sorry, excuse me? No, ZP underline is just the spectrum of, so just the ring space with topological space ZP and a sheaf of continuous functions on ZP. Okay. Yeah. So I don't know, it's yeah. If you want, it's a, okay. No, that's actually an adic space. Okay, so it's even a perfectoid space. I mean, just because CP is perfect. Okay. So now we can okay. So now what can we do? Okay. So second example. So that second example, I will work on the torus instead. So I consider this algebra, CP t minus 1, okay? And its spa is this is like the torus. So these are the guys which have norm 1, okay, in A1, say, okay? Okay, so this is the torus. Okay, and now, well, we can perform this familiar operation of extracting roots of T. Okay, so we can. So again, I start with the algebra of the torus, and then I can extract all roots of T. Okay, all piece roots. Okay. But without completing, and then I can actually complete okay, so this is the p-adic completion. Okay, so the p-adic completion, I really get infinite series with exponent is in z over p infinity and which tend to 0 according to the complement of the filter of finite sets. Okay, so here an element here is some an Tn, where n is in z over p infinity, with this convergence condition I just told you. Okay, and here the series it just stops. So there are not infinitely many denominators in p. Okay. All right. So and now I can again, if you allow me, pass to spectrum. Okay. So here I get something that I want to call T twiddle. Okay, and so this is some kind of perfection of the torus. Here I want to get something I want to call T smooth, which is the uncompleted perfect. I mean, this is the uncompleted inverse limit under multiplication by p on the torus, and then I get some T here, which is there. Okay. So furthermore, I again have an action of Zp of 1 on this tower. So Zp of 1 acts on T twiddle, okay? And in particular, well, let's fix a generator of Zp of 1, okay? So compatible system of roots of unity. Then this generator acts by, well, it will send T1 over p to the n to zeta Pn T1 over p to the n. Okay, so that's again a situation that is similar to the preceding situation in the sense that I have an action of Zp, yeah, on some space here, which is okay. I mean, yeah, so it's quite similar. But now let's look for the locally analytic vectors. Okay, because we've considered the smooth vectors, and so let's try to see if there are any locally analytic vectors. Okay. But there are no. So the proposition is that if you look at Cp t plus or minus 1 over p infinity, so this space of completed functions, and you look for the locally analytic vectors, these are just the smooth vectors. Okay, so very different from above, where there was really a difference. Here you don't get more. So the proof of the proposition is quite easy. Okay? Actually, I can define Tate traces. Okay, so I can define traces. Okay, these are some Tate traces, but it's so explicit that. So what are these traces? Well, you just have your series with infinite exponent and you truncate. So, okay, so you have your sum of the A and Tn, where n is in z over p infinity, and you just map it to sum of the A and Tn, where n is in z over p to the n. Okay, so just this truncation. But well, experts will recognize that. I mean, if you know how Tate traces work, these can be also obtained by considering normalized traces. Okay, and well, and now so it's clear that if I take some element in my ring, then it's really the limit of its Tate traces. Okay. Okay, I mean that's clear. Okay, now let's assume that this element is actually p to the r Zp analytic. Okay, sorry. One important thing I didn't say is that these Tate traces, they are actually Zp equivalent. Okay, so now let me take this guy, which is p to the r Zp analytic for some r. Okay, then actually, if I look at the nth trace of f, okay, huh? Yeah, it's Zp of, okay, Zp of 1, yes, Zp of 1, yeah. So if I look at the nth Tate trace of that guy, you can easily see that this is again p to the r Zp analytic, because you just apply, okay, since it's p to the r Zp analytic, it means that the orbit map is some analytic series. You just apply the trace to all the terms in the series. Those traces have norm 1, and so after you apply the trace, you will still get converging series, okay? So this is p to the r Zp analytic, but this is also smooth, right? Because it's, this is a smooth vector, right? Because it's in there, right? But so if you're p to the r Zp analytic and smooth, it means that you're fixed by p to the r Zp, okay? And so that easily implies, it's a one-line argument, that actually trace n f is equal to the trace r of f for all n bigger than r, which is also equal to f, okay? And so this is how you prove that f is actually smooth, okay? All right, so we see two different situations. So what's really happening? What's the difference between these? Okay, now yeah. Ça va? Okay. It's tempting. Huh? So what's the difference? Well, so the difference is that ah, ok. Ouais. Non, c'est bon, c'est bon. So the difference is that example 1 is an unramified situation in the sense that those guys, let's say pro-étal tower over Cp, Zp pro-étal tower, it has an unramified integral model, because I can just replace these continuous functions from Zp to Cp by continuous functions from Zp to OCP and take formal spectrum, and that will produce for me a pro-étal tower integrally over OCP. Okay? So first example is unramified. Okay? Namely, I can consider the following model. Okay, and that's pro-étal, integral. The second example is, on the contrary, completely ramified. Okay? Because if I reduce mod p, okay, well, so if I reduce modulo the maximal ideal of OCP, what I'm doing, so now if I add the functions on GM. Okay, let me write it. So second example is totally ramified. Okay, so this means that if I look at Fp bar, I would say the reduction of the function of my torus modulo maximal ideal of OCP, this is Fp bar T minus 1, and so the reduction of the perfection, so of this perfect, OCP T plus or minus 1 over P infinity, this is the perfection here, okay? So, okay, well, and so it's completely ramified. Okay, it's a perfection. Okay, and so we learned from this example that if you're unramified, you tend to have many locally analytic vectors, and if you're very ramified, you tend to have few locally analytic vectors. They tend to be all smooth. Okay, all right. So now, building on this toy example, let me now explain the situation for Shimura varieties. And as you will see, for Shimura varieties, the situation is a mixture of both toy models. Okay, so it's, yeah, I mean, or maybe unless you're in some exceptional case, but yeah. Well, or you're not really a Shimura variety, let's say. Okay, so now the case of Shimura varieties. So, but it turns out that even to phrase the theorem, I need the Hodge-Tate period map. So I cannot phrase the theorem without introducing the Hodge-Tate period map. So let me do this quickly. So okay, so I have this Hodge-Tate flag variety, which is G over P mu, but okay, if we are doing a modular curve, this is again P1. Okay, and then I have this map. So there's the theorem of Cariani and Scholze. So saying that there is an Hodge-Tate period map from this perfectoid Shimura variety to the flag variety. Yeah. Okay. Maybe okay. Let's say that we're in the Hodge-Tate case or abelian case. Okay. So there exists such a map. Okay, which is GQP equivalent. Okay, so let me, I mean, I'm sure you've already heard about this, but let me just do the example of the modular curve, just for those of you who maybe need some refreshing, refreshment is not the correct word, probably. Yeah, okay. Okay, so let's do the modular curve. Then in that case, this SKP, this is, I think it's fair to think about it as the moduli of elliptic curve together with a basis of the p-adic Tate module. Okay. On the other hand, you have the Hodge-Tate period map. Okay, so I don't have time to define it, but the definition uses some elementary considerations of finite flat group schemes. Okay, so that's the Hodge-Tate period map. And well, now you can use your trivialization and linearize that map. So we can linearize. Okay, and use the basis. So now that we get a free rank 2 module, and with a map to omega e, and now, well, it takes some work, but this map is surjective. Okay, and since this map is surjective, you have a rank 1 quotient of a rank 2 vector space. Rank 2 module, free rank 2 module with a basis, and so this gives a point of the projective space. Okay, so this is the definition of the map. All right, so, but still to define, I need to say just a little more things. Okay, so, right, so I need one more thing. So on this Hodge-Tate variety, on this Hodge-Tate flag variety, I do have an action of the Lie algebra. Okay, because this flag variety is G mod P mu, okay? And so if you have a function on the flag variety, then you can, and if you have an element in the Lie algebra, okay, then you can let your element x act on f by the following formula: d over dt t equals 0, f of exponential tx. Okay, And so that's, I mean, because I'm using that G was acting by translation on G mod P mu, and so I get an action of the Lie algebra. Okay, and actually this action can be used to describe the tangent sheaf of the Hodge-Tate flag variety. Okay, so let me now define G0 to be the constant vector bundle with fiber G. Let me define P0. So this is the subbundle with fiber with Stoke at X. So voilà. So its Stoke at some point X in the flag variety will be X minus 1 Px, right? So this is the moving parabolic. And let me define U0 as the moving unipotent. Okay? Right? So I'm using the modular interpretation of G over P mu as the space of all parabolics of type P mu. And so over each point X, I can put the Lie algebra of that parabolic or the Lie algebra of its unipotent radical. And this defines for me vector bundles. Okay, and now it's a short exercise it's an exercise, so to see that actually the map, so this action of G I define, which is clearly an action by derivation, induces a map from G naught to the tangent sheaf. Okay, so this is the sheaf of derivation. Okay, and this map factors through an isomorphism if I mod out by P0. Okay, and so that's a description of the tangent sheaf of the flag variety. It's G naught mod P naught. Okay, and it shouldn't be a surprise because, for example, if you take the Stoke at the identity, then you know by this uniformization of the flag variety that the Stoke at the identity should be the Lie algebra of G over the Lie algebra of P, which is exactly the Stoke at the identity of that guy, right? So I think that makes sense. All right, so that was a digression, and now I can state the first theorem. Okay, so this is the kind of result that were first proved by Luepan, and then generalized, notably by Rodriguez Camargo, and so the theorem is that, so the first theorem is that the action of G on the locally analytic Shimura variety, so by this I mean on the locally analytic vectors, okay, on the sheaf of rings, okay, it makes sense because it's locally analytic, so I can differentiate the action. So this action of G induces an action of G naught mod U naught, okay? So, in other words, the action is not faithful, right? There's a kernel for the action, and this kernel is exactly that U naught. Okay, I mean, well, it will turn out to be exactly, but at least for the moment, I can tell you that in the kernel there is this U naught. Okay, so let me make this a bit more concrete in the case of the modular curve. Sorry? Yes, sorry, I changed notation. SKP, yeah? Is that right? Yeah. Okay. Okay. Okay, actually, no, maybe this was not the best idea. Okay. So it is, okay, so, yeah, so let me try to be a bit more concrete about this in the case of the modular curve. So that theorem is really telling us that the locally analytic vectors, they satisfy certain differential equations, but these differential equations are a little bit difficult to see because they have coefficients over the flag variety, okay? So they involve element of the group or of the Lie algebra of the group, but their coefficients are themselves element of the flag variety, okay? So, but let me give you the example, the following example. So I take again the modular curve, and I have my Shimura variety over P1, and let me work over the locus where I have some coordinate, okay? And then let me take the pre-image of that locus. So maybe let me call it U. So let me work over that pre-image. Then if I did my computation right over, sorry, actually no, sorry, excuse me. Okay, I'm sorry. I forgot to say something, which is, but okay, sorry, excuse me. Okay, I should have said this before. It's that, I mean, it's not very, but so this Hodge-Tate period map, it actually factors through the locally analytic vectors. Okay, so that was of course implicit in my formulation here, and the proof is just that actually on the flag variety, okay, I have some the action of G or even of G of QP on the functions on the flag variety is locally analytic. Okay, which really is clear, but I even wrote some computation. So please, in the notes I've written some explication of why this action is locally analytic. But really in the case of P1, you're basically acting by homography. And just imagine that if your elements of your group are sufficiently close to the identity, then this homography you can expand into power series, right? And then this power series expansion will immediately show that the action is locally analytic. Okay, but my apologies for this, but therefore I have this factorization, and this is implicitly used. I guess it's implicitly used in this theorem because I mean, it will become clear here also that I really need this coordinate x to be in the locally analytic vector. So, but anyway, so in this example, what's the differential equation over P Hodge-Tate minus 1 of U? We have a differential equation, okay, which is written in the node, but I really think if I didn't make it right, wrong, sorry. I think it's something like this. Okay, so that's a differential equation that's satisfied by the locally analytic vector. Okay, but you see, so these are the elements of the group GL2 of the Lie algebra. Okay, and so they act. But you see that the coefficient involves the coordinate x. Okay, and so it was not easy to guess, right, to find, because it's not. I mean, it would be much easier if these were constant, but this is really not the case. Okay, and so it's not something that you can already see from the group action itself. Okay, it's all right. So. Okay, so let me, so that's the first theorem. Okay, I will, there's actually a slightly more precise version. Let me try to give some intuition for why this theorem is true.
What is the equation?
So the differential equation, I mean that this is a basis of U0. So I mean that this vector generates So it belongs to U0 of my open, okay, there are many U's, so let me call it maybe W. Okay, so this, I claim, I mean, if I did the computation right, this is an element of U0 of W, okay, and it actually generates this sheaf, which has rank 1 in the case of the modular curve. It's a generator of the sheaf, okay? And so this guy annihilates OLA of pi Hodge-Tate minus 1 of W. Okay. All right. So yeah. So maybe let me.
So for x equals 0.
For.
Ah, no, sorry.
Well, I mean, yeah, exactly. Well, this is what I'm going to do actually now. I'm going to convince you that the differential equation holds when x equals to 0. But it's, yeah. But so really, I mean, you should think what it's telling us is that it's, so indeed it's kind of a mixture of the situations we've seen before in the two toy examples, right? Because it's not entirely, I mean, there's, like in the example of the torus, everything was annihilated. I mean, all the locally analytic vectors were annihilated by the Lie algebra, okay? And so it was, yeah, okay? And in the case of the I mean, in the case of ZP underline, then actually there was no differential equation, no non-trivial differential equation satisfied by the locally analytic vectors, okay? And here we are like, we have a mixed situation, okay? So, but let me try to huh?
Can you relate it with your first theorem of the Eichler-Shimura decomposition of?
Yeah, but this is next talk. You mean the relation with the p-adic Eichler-Shimura? Yeah.
Molar forms.
Yeah, this will come. Okay. Let me try to give some intuition for this first. Okay. I mean, so, yeah, you're going too far ahead, I think. Okay. So let me try to give some intuition for this. So let's do the modular curve case. Again. Okay. So now I have this SKP, okay, over the flag variety, which is P1, okay, maybe SKP, really the perfectoid guy. And let me pull back to infinity. Okay, so infinity is like, maybe, I mean, depends what's your infinity, but infinity could be like setting x equals 0. Okay, and so I get some space over infinity, okay? So over SKP, I really had I have an action of the full GQP, but since now I'm looking at the Stoke over infinity, which is only stabilized by a Borel, here I only have an action of BQP. Okay, so that space has an action of BQP. But actually, this is a very familiar space. So let me describe this space for you. So this SKP over infinity, I can first mod out by the unipotent radical of ZP, okay? And then I can mod out by the entire ZP point of the Borel. Okay? So I mean, let me pretend that, well, let me do this, and now let me describe what I get for you. So this would just be the ordinary locus of the modular curve of level, let's say Kp GL2ZP, okay? That would be the Iguza tower that was used, for example, by Ida to construct this theory of ordinary modular form. And that's the perfection of the Iguza tower. Okay? And now, well, people who have studied the Iguza tower know that the Iguza tower extends integrally. Okay? This is unramified. Okay? So on that chunk, you really expect to have lots of locally analytic vectors. This is unramified. But that chunk is a perfection. And actually, if you complete at a point and use certain coordinate, you're literally in the example of the torus I gave before, except that maybe now you have a formal torus and not a, well, this convergent torus, okay? And so, but from this, and if you believe my toy examples, then we kind of convince ourselves that the Lie algebra of U, okay, is going to act trivially. Is going to act trivially on the locally analytic vector. Okay? And that's exactly what the theorem is telling us, right? Because here I'm at the Stoke at infinity, and so the Stoke at infinity of U0 is really U. And okay, and so that way I can prove easily for modular curves the differential equation over P1 QP. But what's kind of magic about this theorem is that you're kind of also going over all the non-ordinary locus where you don't have like this very explicit and nice structure that you can have on the ordinary locus, right? So I would say that this U0 is maybe following the perfectoid direction in some sense, which turns out to have a real meaning at ordinary point, because it's really that chunk that you perfectize, and yeah, and then, okay. So I guess that's the intuition. Okay, but now the result is even more precise, because for the moment I've kind of told you that there is one differential equation, but maybe you could have more. Okay, you could ask. I mean, well, is there more? Is there? Maybe I'm writing this, but actually it's killed by all G0, right? Well, at least, well, I guess my example here shows it can be, but okay. So, but we're still in good way. So let me complement. Ah ouais, j'ai commis une erreur. Encore. Okay. So, okay. So, well, so first now let me say that I can define the diagram. Okay, I think all the terms are here. So now, okay, so let me rewrite my diagram. So I have the locally analytic Shimura variety. It maps to the Hodge-Tate flag variety. But now I understand that on both sides, I have an action of G0 mod U0. And so let me mod out. Let's say maybe modding out by G0 mod U0. So here I get, I mean, at least this will receive a map to, I mean, so if I kill, I mean, if I mod out by G0 mod U0, so that means I kill, I mean, I look at vectors which are killed by the action of the Lie algebra, and therefore I get the smooth vectors. And here I get that space that I denoted by FL de Rham twiddle, and this is really FL modulo G0 mod U0. Okay, and so this is just last time. I mean, I defined the de Rham stack, and so the de Rham stack would really be that you consider FL and you divide by G0 mod P0, okay, which is the tangent sheaf. And so this is a bit bigger. This is some twisted version of the de Rham stack. And if you know things, I mean so sheaves on the de Rham stack are D modules, and sheaves here are, I mean, here you also have the so-called twisted D modules. So there's more freedom. Okay. All right. So okay. So now okay. And so the theorem is that this diagram is Cartesian. Okay. So actually, this theorem appeared in the thesis of Yuan Yang Zhang, and and also I think in work in progress of Anschutz, Arthur César Lebras, Rodriguez Camargo, and Scholze. And probably they also have more general things, but okay. So, okay, so this diagram is Cartesian. Now I'm going to tell you what is the key. So the key fact, and the key fact is really going to tell us precisely the structure of that guy. So the key fact is that so if I take the fiber product of SKP over the smooth vectors of SKPLA, this is really SKPLA times the fiber product of the Hodge-Tate flag variety with the Hodge-Tate flag variety over the Rham, this twisted the Rham stack over, okay. So, I mean, if this diagram is Cartesian, it's an exercise to deduce this. I mean, it's a one-line proof, but let me now tell you what this really means. So what does this mean? Okay. Well, so what it means is actually not so complicated. So, okay, so let's start with the locally analytic vectors. Okay? And so because these are locally analytic vectors, I have a germ of orbit map. Okay, so I can consider the orbit map. Okay? And so this orbit map goes through the function, so OG dagger, tensor OLA SKP, where G dagger inside G, this is the like maybe this is the neighborhood of 1 in G. Okay? So you see if you are analytic of some fixed radius, then you're allowed here to put some fixed neighborhood of G. But since you're only locally analytic now, I mean, if you take them all, then you have some germ. You just have functions here, which means that you have germs of functions on G. So, I mean, yeah, like you're close to the identity, but this map is really F goes to GF. Okay, where I mean, to F you attach the function G goes to GF. Okay, where G is an element of the group in some neighborhood of the identity. Okay. So now let me start to use the other blackboards. So the differential equation tells us that this map is actually going to factor through so this orbit map knows about the differential equation. And so it's going to have this factorization. Okay. Okay. Yeah, okay. And then now this equality is telling me that I can linearize that map over the smooth vectors, and this becomes an isomorphism. Okay, so maybe this is fairly incomprehensible, but what I think this means is the following. At least I like to think of it in that way. Well, I mean, if you have a Galois extension, it's a common thing to tensor your guy over the base guy, and then you usually get functions on the Galois group. And so the way I like to think of this formula, okay, and maybe, okay, I should not be recorded for saying this, but it's in some sense, it's that maybe, I don't know, okay, that maybe this map can be thought of being this kind of Galois with group, the groupoid or the Lie algebroid G naught mod U naught. Okay, I think it's maybe a way to think about this formula. Okay, so yeah, and No, so you see here the tensors were over CP, but the differential equation is not over CP, it's over the flag variety. And so I need to introduce the flag variety. Ah, sorry, this one. Okay, thanks. Yeah, absolutely. Sorry. Thanks. Mm-hmm. Okay. All right. Okay. So now I have kind of 5 minutes. Correct? Yeah. Okay. Okay. Well, anyway, so we have this diagram. Yeah. So yeah, I mean just to say it one more time. This equation really means that, okay, how do I get the locally, can I describe the locally analytic vector over the smooth vector? And the answer is yes. And what you need is basically to add, okay, in the case of modular curves, you need to add three variables, for example, okay? Yeah, okay, but maybe the session question will be a good moment to discuss this, okay? All right, so now, application. So we can use these two. So now from that diagram, I have a sheaf, I have a functor from quasi-coherent sheaves on these on this twisted Rham stack of the Hodge-Tate flag variety to sheaves on the smooth Shimura variety. Okay, but okay, this functor is not mysterious. Okay, because what's a sheaf there? So a sheaf there is a sheaf on the flag variety. Okay, and then I need an action of G naught mod U naught. So what this means that I have this sheaf, I have an action of the Lie algebra of the sheaf on the sheaf. Okay, and moreover I'm asking that the action, so I can linearize the action of the Lie algebra to get an action of G naught, and I'm asking that U naught is acting trivially on the sheaf. Okay. So that, I mean, if you know this, that means that F is some kind of universal, I mean, as an action of the algebra of universal twisted D modules. And in particular, if instead of U naught you're killed by P naught, then it just means that F is a D module. Okay? So I do this, and how is defined my functor? Then so to F, I attach VB of F, which is just did that thing. So you tensor with the locally analytic Shimura variety over the flag variety with F, and you take the vectors. I mean, you take the vectors which are killed by G. Okay, right. Okay, and so this is Okay, so you take the smooth vectors, and the condition that U0 equals 0 is actually ensuring that guy is big enough, in the sense that if you tensor back that guy over the smooth vector, so this VB of F over the smooth vector, then you get back the original thing, pull back to the locally analytic Shimura variety. So in some sense, the condition of being killed by U0 is an admissibility condition. Okay, this really looks like some equation in period rings where the period ring would be these locally analytic vectors. All right. Okay. 5 minutes is okay? Yeah? Sorry, I mean. Now, yeah, let me just now give examples. And yeah, and I will stop here. So examples. Okay, so I do modular curve. So first I have those O of k, okay? And well, this belongs to sheaves, okay? So those O of k, they are actually G equivariant sheaves, and so they have an action of the Lie algebra. And well, if we apply the functor to this O of k, unsurprisingly, we get back the sheaves of modular forms. Okay? But now I'm allowed to work. So the flag variety, so which is P1, I can really write it as a union of two Brouwer strata, okay? And I'm also allowed to work over each Brouwer strata. And so my final claim is that, okay, and it's really an exercise, is that actually over each Brouwer strata, the sheaves O of k that I restrict to this Brouwer strata can be deformed or interpolated. Can be interpolated. Can be interpolated to a family of sheaves O lambda restricted to CW dagger, which belong to this category of twisted, twisted D-modules, O lambda, and now for lambda in CP. Okay? And if you pull back these sheaves and take their cohomology, you get this higher Coleman series. And George will tell you a little bit more about this next time. Okay, sorry, thanks.